Welcome, this is Ad Emmen reporting from the EIG workshop in Sofia. And we're here with Peter Bauer, who gave a presentation about weather forecasting and the simulations for weather forecasting. So welcome.
Thanks so much, Ed. I'm very happy to be here. Sofia is a very nice place and this is a well-organized event bringing together national representatives involved in HPC, so high-performance computing strategy, and how to handle big data in the future together with application owners like us. I'm Peter Bauer. I'm the Deputy Director of Research at the European Centre for Medium Range Weather Forecasts. ECMWF is an international organization that sits in Reading in the UK. It's an international and independent organization that was founded by its member states in 1975 to centralize scientific excellence, but also resources in a single place to provide medium-range forecasts that are much better than any national weather service could perform. Since then, this concept has been proven successful because ECMWF is leading medium-range global weather forecasts. So despite that success over 40 years, we're reaching now a period where realizing the ever-increasing forecast skill requirements by member states of the global community on future computers becomes increasingly difficult. This is because our codes become more and more complex. We want to invest in spatial resolution that allows us to represent physical processes with more and more accuracy. We want to invest in complexity because eventually we have to represent the entire complexity of Earth system processes in a single forecasting system, from atmospheric processes but also atmospheric chemistry, not only physics, ocean processes, sea ice, land surface processes, and the interaction of all these components in our system. We also invest a great deal in ensemble prediction. Ensemble prediction is something that has been founded by the meteorological community to also forecast prediction uncertainties. So not only a prediction of a temperature or precipitation in a place, let's say, but also the uncertainty of that prediction. And that changes a lot depending on how good your model and your initial conditions are, of course, but also on regimes. In certain regimes, forecasting temperatures in Sofia for the next 10 days is easier than in other situations, and we need to assess that to provide our users with a feel for the probability or the likelihood of events and give them confidence in their decision making. So all these investments in resolution, complexity and ensembles require enhanced computing. And our models become more and more complex and more difficult to run on the current HPC infrastructures. And this is why we need a concerted investment in improving our models, at the same time investing in computer code developments, and together with high-performance computing industry and experts to also improve the hardware side of this coin. So it's a real co-design effort that we need to invest in to be able to run our models with much enhanced prediction skill, but at affordable cost even in 10 years.
How are you working on that? Are you starting new projects or?
We understand the challenge as something that cannot only rely on individual small research projects, but that needs a comprehensive effort actually. And for this purpose we have founded a so-called Scalability Program at ECMWF about 5 years ago, where we said it's not just a small-scale effect looking at a particular aspect of the forecasting model, let's say, to make it run faster, but to look at every individual aspect of the entire chain between receiving observational data, dealing with increasing volumes of satellite observations, for example, making the model faster, but also producing our forecast products faster for our member states and users to use. So this entire chain needs to be improved, so it requires mathematical changes, coding changes, it requires workflow changes, and as I said earlier, it requires a tight collaboration between mathematical or algorithmic developments, workflows, but in the end we also have to put this on computers that are changing architectures right now. So we're aiming for a moving target, so we need to make sure that we can run these codes on today's technology, but also on technologies that we will expect in 10 or 20 years.
Speculating, do you expect that there will be different kinds of architectures for different kinds of applications in the future?
Well, there's right now this discussion between general purpose computing and domain-specific computing. I guess general purpose computing is what we had in the past. So we had single type architectures like x86 CPUs that served everybody sufficiently well. That scaled according to the increasing requirements of most applications, let's say, following Moore's law. That appears to be coming to a halt now. New technologies appear. We have processors coming from different types of users, like GPUs, for example, FPGAs, other types of CPUs. We need to make sure that we can exploit those. Some of them promise the same type of, or even better computational performance at much lower power cost. This is something that we need to exploit given our specific requirements. And the investment that is needed for making our codes work on these type of architectures require, again, us investing research in programming models. So one thing is to develop the physics that you put in code and that you want to run on any type of machine. But then some of these architectures require specific programming models to be able to exploit the specific features of that architecture, and we need to invest in that. And this is not something an application owner can do on its own. It needs to be done in a concerted effort, so-called co-design. So the Scalability Program started in 2013. It has gained significant momentum since then. It's strongly supported by ECMWF's member states. We have succeeded in acquiring, participating, but also coordinating a number of externally funded projects. These projects are funded by the European Commission's Horizon 2020 projects. And as I said earlier, they focus on many different aspects like algorithms, programming models, workflows, and these things. What we realized when we discussed this entire complex within our community is that to really redesign forecasting systems, entire forecasting systems that is, within an entire community requires a much larger effort. And we have formulated this now in a proposal to the European Commission for a future flagship initiative. Flagships are very ambitious science projects that the European Commission is supporting. They are 10-year projects. They try to unite entire communities to perform fundamental scientific research and perform structural changes in Europe, serving European society. Examples are the Human Brain Project, the Graphene Project, the Quantum Technology Project, for example. And recently the European Commission has drafted another call for ideas for a new generation of flagships. And our community has responded to that and formulated an idea that is called Extreme Earth, that focuses on, as I said earlier, this entire revision and renovation of forecasting systems, focusing on extremes in the Earth system, hence the name. So it focuses on extremes forecasting because extremes are very impactful. Just think of the hurricanes that affected last season and hurricane season in summer-autumn. Large parts of the southern United States, just two of them, Harvey and Irma, caused 300 billion worth of damages. So extremes like this, but also droughts, earthquakes, volcanoes are extremes of the Earth systems that we need to predict with much enhanced reliability in the future. And the Earth system aspect of Extreme Earth brings together what we do in the atmosphere, ocean and sea ice with the solid Earth community. So this reflects on the volcanoes and earthquakes aspects of it. So this idea brings together these type of applications with high performance computing as the main enabling technology, and with high performance computing we mean the actual computing aspects and the technology that I've mentioned earlier, but also the data issues, dealing with large volumes and very diverse types of data in the future from the entire Earth system, how to manage that, how to make this information available so that users across the community, but also downstream communities like the energy sectors, the food sectors, risk assessment, risk management, national agencies in that context can use the data in a much more efficient way.
Thank you very much for this interview.
You're welcome.
This was Ad Emmen reporting live from Sofia.